These are your 8-8 notes, last type of factoring, and I apologize for the quality of them, but I just didn't want you to watch the old notes. I used to go into too much detail, and I want to simplify this for you guys. And so bear with me. Last type of factoring, this is when we would FOIL, and instead of keeping them separate, 4 terms or 3 terms where they went together, they actually went together, but when they went together, they canceled out. So if you remember, like you might have an x squared, and then you might have a minus 3x and a plus 3x and a minus 9. And then these two went away. And so all we were left with is these two numbers. If you look at those two terms, they're both perfect squares. Okay, x squared is perfect because it's even. So any variable that is a perfect square is even. That means that you multiplied two of the same thing together, and so then when you times it by 2, it gives you that even exponent. So variables are perfect if they have an even exponent. Numbers are perfect if that when you take the square root of them, they give you a whole number. So we're on the next page, we're going to go through all of the perfect, like the first 10 or so perfect squares, but you can use your calculator to figure out if it's a perfect square. The term difference means subtraction. So when you are left with the difference, the subtraction of 2 perfect squares, this is how we're going to factor. It's really just a memorization thing, no work to be shown. And so you just have to remember, oh yeah, I remember when these happened, and what we FOILed together, they weren't opposites, but we called them conjugates. And it was where the opposite sign in the middle created that plus 3x and that minus 3x and then the minus 9. And so this is just all you're going to write. You're just going to memorize what that factors to, what we had beforehand. So this should be a pretty easy day. So the clue that you have it is that there's 2 terms and it has to be a difference, okay? And they have to be perfect. So what is the difference of perfect squares? The product of 2 binomials, when we multiply 2 binomials, when the outer and the inner terms cancel out, leaving only the first and the last term. So that's what we have. We have the first term and the last term, and they're both perfect squares. How to factor them? We're basically going to ignore all of those little dots, and I'm going to write this down. A squared minus b squared. Not using numbers because it can be any number. A can represent any number, any variable. B can be any number and any variable. And when we factor them, we take the square root of the first and the square root of the second. One's positive, one's negative. And so I know I didn't show my work of taking the square root, but that's how a squared turns into an a to the first. You'll see on the next pages how this applies. Okay, so the first thing we have to do here, oh, I think I have to go back though. There it is. So on this right here is our first 20 perfect squares. Let's go ahead and put them in here. Then we have them. If you forget your calculator, you have them. But also, it just kind of get them familiar to you. And I'm going to try to make my pen a little bit not so fat. Oh, I think I'm as thin as it can be. All right, so for 1 squared, it's 1. 2 squared is 4. 3 squared is 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, okay, this can go away, 169, 196, 225, 256, 289, 18 squared is 324, and 19 squared is, oh, this one I don't remember. I want to say 491, 591, I'm not sure. Let me do the math real quick. Oh, I was way off, 361. Oh yeah, and then this is 400. So also the first 20, you have them, but you remember if you ever get stuck and you need to know what the perfect square or just see if it's a perfect square on your calculator, you can type it in square root of 225, and if it gives you a whole number, you know you're dealing with a perfect square. The perfect square variables, I told you a variable is considered to be perfect if it has an even exponent, okay? Divisible by 2. And to take the square root of it, you actually divide by 2. Okay? So x squared is perfect of x. X to the 4th is perfect of x squared. Okay? Because x squared times x squared would give you x to the 4th. We add the exponent. So you just divide by 2. So technically, x to the 10th. So don't look at this number and think that it has to be in this list up above. 10 is not a perfect square. If you take the square root of 10, you're not going to get a nice number. But 10 is even. And so what that tells me is that x to the 10th was a perfect square. Somebody multiplied x to the 5th times x to the 5th. If you recall from chapter 7, that means we added the exponents. So when we take the square root to undo this x to the 10th, we don't really show our work like that, but you just divide by 2. Okay, so this is the little trick that you're going to memorize. You're going to divide by 2 to take the square root of it. So x to the 10th is a perfect square of x to the 5th. So if it's an even exponent, it was what you have to know there. All right, so let's go ahead and try some of these on the next page. You have 2 questions to ask yourself. Okay, first question. Do I have a difference? If it's adding, it doesn't work. There's no such thing as a sum of perfect squares. So do I have a difference? That's why they call it a difference of perfect squares. They want you to know that that's an important part of that. So in number 1, yes, we do have a difference. Number 2, are they both perfect squares? Are they perfect squares? So this is what we're going to do. We're going to count the terms. And when we have 2 terms, we're always going to look for GCF. That's the very first thing we do. No GCF here. I see that it's subtraction. We have a difference. M squared is an even exponent that is perfect of m. And 64 is a perfect square of 8. And so I know what they multiplied to get this was an m plus 8 and an m minus 8. You really have to channel chapter 8, part 1, when we did this, when we FOIL these. Okay? It's complete memorization here. I don't want the work. I want you to recognize those. These will get you at first because you're not going to remember them, but as you get used to them, they actually become one of your favorites because it's the least amount of work. If you look at number 2, do I have a GCF? No, the first one has Y's, the second one has Z's. 16 and 18, I could try a bunch of numbers. I could try 3, 9, 6, 8. None of them are in common, okay? So we look for GCF. They are a difference. They are subtracting. And they are perfect squares. Okay, so I'm going to take the square root. So all I know is I know I'm going to have parentheses times parentheses. One's going to be positive. One's going to be negative. Now, I don't know if I recommend doing what I just did there because you're kind of limited to your space now. And so you end up with, sorry about that. I don't know what that was. There we go. So I got to take the square root of 16. So that's going to go here. That's 4 and 4. The square root of y squared, we just divided by 2, y and y. That's what we multiply together to get y squared. 81, the square root of 81 is 9. So those go in these spots. And then z squared is z. And you just factored a difference of perfect squares. We always look for more factoring, but 4y and 9z don't have anything in common. Okay, third one here, x squared minus 49. No GCF. If there was, I'd take it out. Difference, it's a subtraction of perfect squares. And so I'm going to have x squared is perfect of x, and 49 is perfect of 7. I tend to put the plus first every single time. I don't know why. Other people like the minus first because they see the minus. It does not matter. You need one of each. You need an x plus 7 and an x minus 7, and then you're done. Number 4, is there GCF? No. Is there a difference? No. If there's no GCF and it's not a difference of perfect squares, this is what we call prime. Now you haven't seen that yet. I haven't shown that yet. And that means you can't factor it. Prime means cannot factor. There's nothing I can take out of either of those to make it work. There was no product. I can't show you multiplication. That was just it. So think of another prime number. 5 is prime. 5 cannot be factored. If I made a factor tree, the only branches of the factor tree would be 1 in itself. That's not factoring. It's still itself, right? It's still 5. Some people argue, well, what if you did x plus 5 times x plus 5, right, to get that plus sign? This is going to give you outer inner. It's going to give you a trinomial. This is going to give you x squared plus 5x plus 5x plus 25. Okay, so these two plus 5x's would make a positive 10x. Someone might say, okay, well then do negative. That's just going to give you a negative 10x in the middle. It won't go away. In order to make them cancel, you have to have one positive and one negative. And if you have one positive and one negative, always you'll get a negative when you multiply them. This is a positive. So there's a contradiction there. So on these answers, we write prime. I usually tell you, because they're very frustrating, you're trying to factor, and then I tell you, oh, you can't factor that one. So it just adds another dimension to these problems. You're also going to start seeing some other things, like some factoring of a GCF and that sort of thing in there too. So we'll kind of working that in there. This is an easy way of factoring, so that's why we do that here. Lesson summary, we're going to call it good. And go ahead and try to factor this difference of perfect squares. I'm going to give you a little bit complicated one here, but not too bad. There. Good luck.